On July 23, 2012, the Sun launched one of the most powerful solar storms ever recorded. It did not hit Earth. It missed us by about 9 days. That single detail may be one of the luckiest facts in modern human history. Because if Earth had been in the way, this would not have been remembered as a beautiful aurora event or a strange science headline. It could have become the day the modern world suddenly discovered how fragile it really is. A solar storm does not look like a normal disaster. There is no shock wave moving through cities. There is no wall of fire crossing continents. There is no giant impact crater. The danger arrives through something more invisible and more unsettling. First, the Sun throws billions of tons of magnetized plasma into space. Then that material races across the solar system. If Earth is in the path, the storm strikes our magnetic field. Currents are induced. Satellites begin to struggle. Radio systems can degrade. Navigation becomes unreliable. Power grids can start taking stress they were never designed to carry. The frightening part is not just how strong the Sun can be. It is how dependent modern life has become on systems that sit directly in the path of that kind of event. When people think of space, they often imagine distance and emptiness. But Earth is not isolated from the Sun. We live inside the outer atmosphere of a star. Everything that powers life here also carries risk. Sunlight gives us warmth. Solar energy drives climate. The Sun makes life possible. At the same time, the Sun is violent. Its surface is not calm. It twists with magnetic tension. It stores energy. Sometimes that energy is released suddenly. When it is, the result can be a solar flare, a coronal mass ejection, or a combination of both. A solar flare is a sudden flash of radiation. A coronal mass ejection, often called a CME, is a giant cloud of charged particles and magnetic field thrown out into space. Not every solar eruption points at Earth. Many shoot harmlessly away from us. Some glance past. A few arrive. The most dangerous events are not just strong. They are strong and correctly aimed. That is why the July 2012 event matters so much. It was not only large, it crossed Earth's orbit. We simply were not there when it passed through. We were lucky, very lucky. To understand why this matters, we need to talk about what would happen if that luck had failed. The first thing to understand is that the Sun does not need to burn cities directly to create disaster on Earth. A solar superstorm is a systems crisis. It attacks the electrical and technological skin of civilization. Our world runs on invisible structure: electric transmission networks, timing signals, communication satellites, navigation systems, aviation routing, weather forecasting, financial synchronization, emergency coordination, long-distance data links. The modern world feels physical because we can touch roads, buildings, cars, and wires. But underneath all of it is a layer of precision timing, orbital infrastructure, and electrical stability. A severe solar storm threatens that layer. That is what makes it so dangerous. And this is not a fantasy. We know large solar storms have hit before. The most famous example is the Carrington event in 1859. Telegraph systems failed. Operators received electric shocks. Some telegraph paper caught fire. Auroras were seen far closer to the equator than usual. At that time, the world's electrical dependence was tiny compared with what it is today. That is the part people often miss. The Carrington event happened in a world that had barely begun electrifying itself. Today, the same kind of event would arrive on a planet covered in vulnerable infrastructure. That alone changes the meaning of the comparison. A 19th century storm in a 21st century civilization is not just a repeat. It is a new category of risk. We have already seen smaller warnings. In 1989, a geomagnetic storm caused the Hydro-Quebec power grid to collapse. Millions of people lost electricity in a matter of minutes. That was not the worst the sun can do. It was a warning shot. In 2003, the Halloween solar storms disrupted satellites, radio systems, and power operations. More recently, even weaker events have reminded scientists and grid operators that space weather is not an abstract curiosity. It is a real, operational threat. So when scientists looked back at the 2012 event, the message was not subtle. We came close to something serious, very serious. The July 2012 storm was observed by the Stereo spacecraft. It was fast, extremely fast. The ejected material moved at extraordinary speed and carried a magnetic structure capable of producing a severe geomagnetic response if it had struck Earth under the wrong conditions. That phrase matters, under the wrong conditions. A solar storm does not create damage by size alone. Its magnetic orientation matters too. If the storm's magnetic field connects efficiently with Earth's magnetic field, energy can be transferred more effectively into the magnetosphere. That is when the danger increases sharply. This is why two storms of similar size do not always produce the same results. Geometry matters. Timing matters. Magnetic orientation matters. Space is full of these uncomfortable conditional statements. And yet the overall lesson remains clear. If a storm of that scale had hit directly, modern infrastructure would have taken a hard blow. How hard is still debated. Some scientists emphasize the worst case. Others stay more cautious. That is normal. The real world is complex. Power grids are different in different countries. Some transformers are more exposed than others. Some satellite systems have more resilience than others. Response planning has improved. But uncertainty is not comfort. It is part of the threat. Because when the event is rare and the system is global, nobody gets a full rehearsal. Now imagine the first warning. A bright solar eruption is detected. Space weather centers begin tracking it. The estimated arrival time is announced. Operators at utilities, satellite companies, and government agencies begin preparing. That may sound reassuring. It is only partly reassuring. The warning time is limited. For radiation from a solar flare, some effects arrive quickly. For the CME itself, there may be hours to a few days depending on speed. That sounds like enough time until you realize what must be protected. Some power operators can reduce load or reconfigure parts of a grid. Some satellites can be placed into safer modes. Some flights can be rerouted, especially those passing near the poles where communication and radiation concerns can increase. But no one can shut down civilization neatly and restart it without pain. Preparation helps. It does not erase vulnerability. And if the storm is strong enough, even prepared systems can still suffer. The first public sign might not be dramatic. For some people, the sky might look normal. Maybe the internet seems slow. Maybe GPS behaves strangely. Maybe some communications cut out. Maybe operators quietly start losing telemetry from satellites. Maybe pilots and controllers are dealing with degraded systems before the public understands anything at all. Then the storm reaches deeper. The magnetic field around Earth begins to shake. Electrical currents are induced in long conductors. Power lines become pathways. Transformers begin to absorb stress they were never meant to see. This is where the subject stops being astronomy and becomes survival engineering. Because extra current in a power system is not just a technical inconvenience. Large, high-voltage transformers are difficult machines to replace. They are expensive, specialized, and not sitting in giant ready-made piles waiting for emergency shipment. If enough of them fail, restoration is not a one-day problem. That possibility is what gives this topic its real weight. A serious solar superstorm does not need to destroy the planet. It only needs to break enough of the systems the planet now depends on. That is the first layer of the story. The Sun launched a monster storm. Earth missed it by 9 days. And hidden inside that near miss was a disturbing truth. Modern life may be far more exposed to space weather than most people realize. If the July 2012 storm had hit Earth directly, the first major crisis might not have been something people could see. It might have been something they only noticed once systems started failing. That is what makes this threat so different from an earthquake, a hurricane, or a flood. A solar superstorm reaches into the invisible structures that hold daily life together. Think about how many parts of normal life depend on precision timing. Banking networks rely on accurate time signals. Cell networks depend on synchronization. Navigation depends on satellite timing. Air traffic, shipping, weather systems, logistics, and emergency coordination all depend on connected layers of data moving across distance with reliability. People often say the world runs on electricity. That is true, but it also runs on stable coordination. A strong geomagnetic storm can disrupt both. Once the storm hits Earth's magnetic field, the magnetosphere begins to respond. Energy is dumped into the near-Earth environment. Charged particles can be accelerated. Radiation conditions around Earth can intensify. Satellites in orbit are suddenly working in a harsher space environment. Some may experience temporary glitches. Some may lose orientation. Some may suffer sensor noise or upset events in electronics. Others can be damaged more seriously, depending on altitude, shielding, and exposure. This matters because satellites are not luxury objects anymore. They are part of the ground beneath our lives, even though they are not on the ground. If enough satellite functions begin degrading, the public could feel it quickly. Navigation errors begin appearing. Communications become less stable. Weather data becomes harder to trust. Some broadcast or military systems degrade. Certain aviation routes, especially at high latitudes, become more difficult to manage. The first thing to fail may not be a city. It may be the invisible system above every city. Then comes the grid problem. Geomagnetically induced currents can enter long transmission lines and flow into transformer networks. The larger and more interconnected the grid, the more pathways there are for trouble. Not every transformer is equally vulnerable. Design matters. Ground conductivity matters. Grid configuration matters. But again, uncertainty does not mean safety. A small number of critical failures in the wrong places can cascade into much larger disruptions. And a cascading failure is where this stops sounding like a technical report and starts sounding like a civilizational test. Power restoration after a routine outage can already be difficult. Now imagine trying to restore power while communications are unstable. Regional equipment is damaged. Replacement components are scarce. Fuel logistics are stressed. And public pressure is rising by the hour. Refrigeration becomes a problem. Water pumping becomes a problem. Hospitals switch to backup power and pray the fuel supply holds. Traffic control fails. Payment systems struggle. Gas stations cannot operate normally. Supply chains tighten. Food spoilage begins. A disaster like this does not need total collapse everywhere to become historic. A partial, long-duration outage across enough regions would already be severe. And the timeline matters. A short blackout is painful. A multi-day infrastructure crisis is something else. A multi-week restoration problem in heavily affected regions could change how people talk about risk for generations. This is why researchers and emergency planners worry about high-impact, low-frequency events. Most days, modern systems work so well that people assume they are normal by default. A rare event can reveal how little redundancy there really is. Now think about public perception. At first, people might hear that a solar storm is coming and picture auroras. That is not wrong. Auroras would likely be part of the story. A strong geomagnetic storm can push auroral displays far from the poles. Skies over places that almost never see them could glow red and green. To people standing outside, that might even look beautiful. But beauty would be a side effect of something far more serious. The same disturbance lighting up the sky could be quietly destabilizing the systems under modern life. That contrast is one of the most unsettling things about space weather. The sky can look magnificent, while the infrastructure below it starts failing. If the event were strong enough, the first emotional phase might be confusion. People notice strange auroras. They hear about satellite issues. Then reports of outages begin. Then more outages. Then the question changes. It is no longer what is happening in space. It becomes, how long is this going to last? That is where the real fear begins. A severe solar storm is not only a physics problem, it is a duration problem. How much is damaged? How quickly can operators isolate failures? How much equipment survives? How many backup systems hold? How many regions stay connected enough to help the ones that do not? And behind that is a harder question. How much of the global economy assumes that this kind of event will probably not happen right now? There is another layer too. The Earth is not hit by one clean wave, and then everything is over. Solar activity can come in sequences. Multiple eruptions can interact. An earlier CME can clear the path for a later one, allowing it to travel more efficiently. That is one reason some historic events become so intense. The sun can prepare the road before sending the bigger blow. That possibility makes the 2012 event even more uncomfortable to think about. It was not just a big eruption in isolation. It emerged from an active solar environment in a way that reminded scientists how extreme space weather can become under the right circumstances. At this point, it helps to correct something important. A solar superstorm would not send humanity back to the Stone Age in one dramatic instant. That kind of phrase is cheap and too simple. Reality is more serious than that, because it is more uneven. Some regions would suffer more than others. Some systems would fail partially, not completely. Some countries are more exposed. Some operators are better prepared. Some satellites would survive. Some networks would adapt. The danger is not one cinematic collapse scene. The danger is a patchwork crisis with enough overlap to become global. That may be worse in some ways. It creates confusion. Partial failure is hard to diagnose, hard to communicate, and hard to repair. It creates false hope in one place and panic in another. One city still has power, another does not. One region still has communication, another loses it. One country can reroute around the damage, another cannot. The world becomes uneven in a way that makes coordination harder. And coordination is exactly what you need most in a crisis like this. Now return to the 9-day miss. That is what gives the whole story its sharp edge. This was not a distant theoretical model built from a star on the other side of the galaxy. It was our sun. It was our orbit. It was an event that crossed the space Earth occupies. We just arrived at that location 9 days later than the storm did. That is the difference between a major scientific near miss and a possible historical turning point. And because it missed, many people have never heard of it. That may be the strangest part. A storm powerful enough to trigger serious global concern if it had struck directly past through Earth's orbital path. And most people went on with their week without knowing how lucky the timing had been. That is what makes this subject feel so eerie. Disaster did not fail because we had conquered it. Disaster failed because Earth was somewhere else. The sun does not care about our schedules. It does not wait for civilizations to be ready. It does not aim in the human sense. It erupts. We happen to be in the way, or we do not. That is the second layer of the story. A direct hit would not simply create a pretty sky event. It could turn the technological shell around civilization into the most vulnerable part of modern life. And in 2012, we avoided that outcome by a margin of days. So what do we do with a story like this? The easy version is to turn it into pure fear. The better version is to understand what the near miss actually teaches. The first lesson is that extreme space weather is real, not possible in some vague science fiction sense. Real, observed, measured, studied. The sun has done this before. It will do it again. The only uncertainty is when the next major event will come, how strong it will be, and whether Earth will be in the path. The second lesson is harder. Our species has built a civilization that is more advanced than any before it, and in some ways, more exposed. That sounds paradoxical until you look closely. The more connected we become, the more systems depend on invisible layers that must keep functioning together. That gives us extraordinary capability. It also creates shared points of failure. A solar superstorm reveals those points brutally. It tests electrical resilience. It tests orbital resilience. It tests communication resilience. It tests whether governments, private operators, emergency planners, and the public can function under degraded conditions. And perhaps most unsettling of all, it tests whether our confidence in normal life was based on real stability or simply on long good luck. That is why this topic stays with people. It is not just about the sun, it is about dependence. The modern world feels permanent because most people have never seen the systems underneath it fail at scale. A strong solar storm reminds us that permanence is often a temporary feeling created by stable conditions. Change the conditions, and the world can feel much less solid very quickly. Now imagine the day after a direct hit. If the storm were severe enough, the headlines would not all agree at first. Some would focus on auroras, some would focus on blackouts, some would focus on satellite disruptions, some would focus on government warnings. Social media would be full of partial truths, confusion, dramatic videos of red skies, and wild guesses about what was coming next. That information chaos would be part of the event. And yet beneath it, the physics would remain indifferent. Currents in wires, particles in space, transformers under stress, satellites in trouble. The sun does not become less dangerous because people misunderstand it. That is why preparation matters. And to be fair, preparation has improved. Power operators understand geomagnetic risk better than they used to. Space weather forecasting has become more sophisticated. Government agencies and utilities have studied severe storm scenarios. Satellite designers think about radiation effects. The world is not asleep, but no serious planner would say the problem is solved. The modern system is too large, too uneven, and too interconnected for that kind of confidence. Preparedness reduces harm. It does not eliminate it. And that is the right tone for this story. Not panic, not fake certainty. Respect. Respect for the fact that Earth lives under a star. Respect for how much of daily life now depends on infrastructure that did not exist during the last truly historic solar storm. Respect for the uncomfortable truth that civilization can be vulnerable in ways that are easy to ignore until a near miss pulls the curtain back. This is also why the subject feels almost unfair. The threat does not come from human enemies. It does not emerge from a hidden bunker or a secret weapon. It comes from the same star that lights our mornings. That contrast is hard to shake. The sun gives us daylight, seasons, and energy. At the same time, buried inside its magnetic complexity is the power to disrupt much of the technological environment we have built around ourselves. That is what makes the 2012 event more than a cool astronomy fact. It becomes a reminder that the line between ordinary life and systemic stress can be thinner than we want to believe. One strong eruption, one different position in Earth's orbit, one direct magnetic connection. That is all it takes for a near miss to become a global event. And still, this is not a doom story. The point is not that civilization is helpless. The point is that resilience is a choice that has to be built before the event arrives. Transformers can be protected better. Grid procedures can improve. Satellite response plans can improve. Forecasting can improve. International coordination can improve. The problem becomes much worse only when people treat rare events as impossible ones. That may be the most practical lesson of all. A risk does not need to happen often to matter. It only needs to happen at the wrong scale once. Now, step back and look at the story in its simplest form. In July 2012, the sun launched a storm powerful enough that, under the wrong conditions, a direct hit could have produced serious global technological consequences. Earth was not there. The storm crossed our orbital path anyway. We missed it by 9 days. That is not mythology. That is not exaggeration. That is timing. And timing may be the reason most people have never had to think seriously about what space weather can do. There is something strangely humbling in that. For all our intelligence, planning, and engineering, some of history still turns on where a planet happens to be when a star erupts. That does not make us weak. It makes us real. We are not standing outside nature looking in. We are inside it. Inside a magnetic environment. Inside a solar system. Inside the weather of a star. That is the final layer of the story. The sun almost sent us a reminder. Not a reminder that Earth is fragile as a rock. Earth will survive. The reminder was aimed at something more recent and more delicate. It was aimed at the civilization we wrapped around the planet. The grids, the satellites, the timing networks, the silent machinery of modern life. That is what might have taken the hit. And that is why this near miss matters so much. Not because it destroyed us, because it did not. Because it showed, for a brief moment, how close ordinary history may have come to becoming a completely different kind of history. The sun fired a monster storm. Earth missed it by 9 days. And hidden inside that fact is one of the strangest truths in modern science. A planetary scale warning can happen without most people even noticing. We were lucky. The better question is whether we will still be lucky next time.